Welcome to Math 2318. This is section 2.7. We're looking at linear algebra applications of computer graphics. So, in question 1, we have a triangle. This is a triangle in the plane, and the coordinates for the corners of the triangle are given here by matrix D. Minus 3, 0, minus 2, 2, minus 5, 3. And so if I draw a little sketch of that, that's here in this picture here on the left, showing us that particular triangle. Now we want to see what happens to this triangle under the transformation that reflects the triangle through the y-axis. So we're taking the triangle and we're wanting to reflect it about the y-axis. Alright, well, what does that reflection matrix look like? Well, let's see. Here's 1, 0, 0, 1. So under the reflection about the y-axis, the 1, 0 becomes minus 1, 0. Nothing happens to 0, 1. So my transformation matrix A looks like minus 1, 0, 0, 1. So the operation would be matrix multiplication. And the operation is defined. A is 2 by 2. My triangle D is 2 by 3. So the resulting matrix will be 2 by 3. And the coordinates represent where the triangle went. And so if you simply go regular matrix multiplication, minus 1 times minus 3, and 0 times 0, we get a positive 3. So just go through each of the rows and columns to figure out what the image looks like. And the image looks like 3, 0, 2, 2, 5, 3. Which makes sense because you're simply reflecting each of these points across the y-axis. And so in the final part of the question there, they asked you, well, what does it look like? Well, we just did that. That was the matrix multiplication. And then there's a pick the right one for what went where. So the black picture here, the black triangle, is the original. It got reflected about the y-axis, and here's the image that we got with our new matrix. Alright, in question 2, we'd like to find a 3 by 3 matrix that's going to do a composition of transformations. We'd like to translate a point by translate all points in the plane by 5, 8, and then we'd like to rotate 45 degrees about the origin. So there's a couple of things going on here. First are these homogeneous coordinates. So if we are in R2, our point looks like X and Y. If we are in R3 with homogeneous coordinates, this is X, Y, and up 1 in the Z direction. So my rotation matrix in 2 dimensions is normally cosine theta minus sine theta, cosine theta. But in terms of homogeneous coordinates in R3, I've got cosine theta, sine theta, 0. Minus sine theta, cosine theta, 0, my X and Y in R2, and then 0, 0, and up by 1. My translation matrix looks like 1, 0, 0, 0, 1, 0, and now translated by h in the x direction, k in the y direction, h, k, and 1. And again for homogeneous coordinates. So the translation by 5, 8 looks like the matrix that we see here. My rotation matrix is cosine of 45 degrees. Our 45-degree triangle from trigonometry, if you happen to have forgot that, is 1, 1, square root 2. So sine and cosine are 1 over square root 2, but when you rationalize it, that's square root 2 over 2. All right, so the composition is in this order because if I have a point, the point would be operated first on by the translation, followed by the rotation. So after that, it's simply grinding through rows and columns to find the matrix multiplication. The last column here is where the shift is taking place. And so that's what our composition matrix would look like. All right, so what's going on here in question 3? Again, we have in R2, we are in homogeneous coordinates. We'd like to translate by -4, 6. All right, our translation matrix looks like the following. We'd like to scale the x and y coordinates by 0.4 and 1.6. All right, so we see those there. Again, you see the last row and column. All right, for the composition, we first will translate, so that's the matrix that appears first, because if I put an x, y, and 1 here, it would operate first under the translation, followed by the scaling. And so again, simply perform the matrix multiplication to find the composition matrix for the two operations. All right, we continue this. What are we going to do? We are going to reflect through the y-axis, which we saw in question 1. So that's -1, 0, 0, 1. Again, the homogeneous coordinates. We're going to rotate by 30 degrees. All right, our rotation matrix in R2. Our 30, 60, 90 triangle. 30, 60, and 90. How did that go? Let's see. It goes 1, 2, square root 3. The sine of 30 degrees is 1/2. All right. And so cosine 30 degrees is square root 3 over 2. All right, so we've got our rotation matrix, our reflection, the composition. We will do the reflection first, followed by the rotation. And so, again, perform the matrix multiplication to find the composition matrix for the two activities in the order that was asked for. In question 5, if you look at homogeneous coordinates in R2, we saw that looked like for R2 was x, y, and 1 in homogeneous coordinates. For R3, extending this, it looks like x, y, z, and a 1. All right, so if I have a point in R3, and these are the homogeneous coordinates, the x, y, and z are given by the x component divided by h. So they gave me the x component, they gave me h, flip the fraction on the bottom and multiply, and we get minus 12. And so if you do that for both y and z, it's a very straightforward problem to figure out what was the point in R3 that had those particular homogeneous coordinates. Okay, looking here at question 6. We like to find the 4x4 matrix that rotate points in R3 about the y-axis through an angle of 330 degrees. Alright, so there's a lot going on in this problem, some clear and some not so clear. First off, let's make the clear part. If we're rotating about the y-axis, that means that any point along the y-axis is not going to move. Alright, second, if we want homogeneous coordinates in R3, then that's why it is a 4x4. And if you remember, our x, y, and z went to x, y, z, and the last coordinate was a 1. So that's why that has to be part of our matrix that does this operation. Alright, that part is somewhat clear. So the homogeneous coordinates part, the points along the y-axis are not changing. That's why you see E2 is remaining in place. It's not going anywhere. So the only thing that's happening is the rotation. Now the rotation seems straightforward enough. The problem is the positives and negatives. So let's take a look at this. If we're looking down the y-axis toward the origin, we are rotating in that direction. Alright, now why is it in this direction? I thought we were going clockwise. Well, it is because here's the positive x, here's the positive y. And so if you want to think of it that way, then what's happened is I'm rotating around the positive x-axis. So from there, around 330 degrees. Alright, so similarly, if I do that in this picture, so what I'm trying to show you is where did E1 and E3 go? So relative to the positive x, positive z, it's really looking like 30 degrees. And so if this is by 30 degrees, I get cosine 30, sine 30, minus sine 30, cosine 30, and we get our 1/2 and minus 1/2 from the sine. Cosine is square root 3/2, and if we fill in our missing parts, then our matrix needs to look like the following. Alright, I wanted to add just a little bit more to my picture, hoping to make this a little bit clearer because it can be confusing. So I'm going to add here was E1. And so if we went clockwise from E1, clockwise is around this way. There's my 330 degrees, and that's why it leaves E1 pointing upward here, essentially in quadrant 1 by 30 degrees. And if you trace here for E2, so here's E3 because it's the z-axis, and you trace it around 330 degrees clockwise, it ends up 30 degrees from the positive z-axis. So again, it's a matter of perspective as to which axis you're rotating about and where's the positive and negative axes. Hopefully this is a bit clear. It can be a bit confusing, again, just because of the direction things are being orientated.